Welcome to part 2 of the tutorial on security and privacy in distributed optimization and learning. My name is Nitin Vaidya from Georgetown University. The slides for this tutorial are available from the website shown here, along with the videos, links to the videos. So visit this page and then click on the tab for talks. So the context for this particular tutorial is cost functions that have this particular form. Sigma fi of x, where I is the index of an agent. The summation is over all the agents in the system. And we're trying to find the argument, the x value that minimizes this global cost function. So fi of x is the local cost function of one of the agents. And as I mentioned in the previous lecture, we will look at two architectures to solve this problem distributedly. One is a peer-to-peer architecture shown on the left, and the other is a server-based architecture shown on the right. So we saw this gradient method last time, and this picture illustrates how one can start at an estimate x0 and then take a step towards x1, then x2, then x3 in the centralized setting. And the way we did that was by using this particular iteration. You have seen the iteration previously in the last lecture, except that now I have made fx to be specifically equal to this particular cost function, where the summation is over agent identifiers I. So if you have three agents, I will be equal to 1, 2, and 3. And so this one iteration of the algorithm is that you have, suppose we are at xk, the estimate, the current estimate is xk after k steps, and we want to compute xk minus 1, then xk minus 1 is xk plus 1 rather. Xk plus 1 is equal to xk minus the step size multiplied by the gradient of the cost function, in this case fx, but the function happens to be equal to the summation, therefore it's a gradient of this summation of fix. Now, if you simplify this just a little bit, then we get that here, the gradient was outside the summation inside, but we can rewrite it this way. So what you really need to compute is the summation of the gradient of these different cost functions. Now, in the system that we're looking at, each agent knows its own cost function. So if I'm agent number 1, I know f1x, the cost function, my cost function. If it is a machine learning, the training problem, then f1x represents the loss measured over the data items that I have available locally. So that's f1x. And so each agent can compute the gradient of its own cost function perhaps, but nobody knows all the cost functions. So the question then is, how do you compute this summation over the gradients? And because no single agent can do this, they have to cooperate somehow to compute that summation, either explicitly or implicitly by some other indirect means. And that requires distributed algorithms. And that's what we're going to discuss today, is how to minimize cost functions of this form in a distributed setting under those two architectures. To simplify the discussion, we're going to assume that each of the fix is a convex function. And so let's get to that. Before I look at specific examples of distributed solutions, I want to point out one small detail here. If you look at this summation here, you can imagine that there is a multiplier in front of each of this function fix, which is equal to 1. And similarly, there's a multiplier 1 here. You're multiplying these functions up in this expression for fx, or the gradients in the expression down at the bottom of the screen by a constant, which happens to be 1. But more importantly, that constant of the weight, which is 1 when I wrote it down earlier, the weight is uniform, meaning we are multiplying all the functions by the same identical weight, uniform weight. Now, if I were to replace those uniform weights, which I said was 1, but there could be something else, alpha, constant. If I were to change that and replace this multiplier here for gradient fi by some other constant that depends on I. For example, alpha 1 might be 1 and alpha 2 might be half. If I did something like that, then the problem is that the function that I'm minimizing will be different. It will not be summation of fix anymore. In particular, if I always multiply gradient of function I with constant alpha I, then the function I'll end up minimizing is actually this one, sigma alpha I fix. If alpha I is non-uniform, then the function I'm minimizing will not be sigma fi of x. That's a very simple observation I want to make, because we are going to come back to this more than once today in the context of asynchronous algorithm, stochastic gradient descent, and so on. So this is a simple thing, but it matters, and you have to be careful about designing distributed algorithms to avoid these weights becoming non-uniform. So uniform weights are important. So these are the two architectures we talked about before, just briefly. So let me begin with distributed algorithms first for the server-based architecture on the right-hand side. And then once we have discussed that, then we will talk about the peer-to-peer system. So when I refer to these kinds of algorithms, I call them all distributed algorithms. But in the literature, there seem to be at least 3 different terminologies used. And this is just my interpretation of what those terminologies are used for. Hopefully I'm right. So when people often refer to decentralized algorithms, they're referring to what I call earlier the peer-to-peer system, in the sense that there is no central entity, such as a server, and the agents are on their own, and they form a network, and they need to solve the problem somehow. The federated and the distributed settings are both server-based, meaning that there is one or more servers trying to help these agents to compute or solve this optimization problem that we defined earlier. But they differ in some small details, and we will go through the details, in fact, in the next 10, 15 minutes. But essentially, the question, what the two differ in is what are the agents computing and sending to the server. So what is the communication from the agent to the server that differs a bit between the two solutions? They're not that different, and yet sometimes people use different jargons for them. Conceptually, they're quite close, at least to me, to my way of thinking about it. So here is the federated architecture. It's a server-based system. So let's say you have one server, and there are many agents, and those agents are going to work with this server to solve the optimization problem. In particular, we want to find the argument that minimizes sigma fi of x. And in our setting, agent number 1, if this guy is agent number 1, he knows f1 of x. If this is agent number 2 knows f2 of x, and so on. And therefore, agent number 1 can compute the gradient of function number 1, and agent number 2 can compute the gradient of function number 2, and so on. So here is the algorithm, very simple. The server maintains an estimate xk. Initially, xk would be k equal to 0, so it's the initial guess the server makes at the argmin of this cost function. And then it's going to update x0 to obtain x1, and then x2, and so on. And so what's the update step that happens in each iteration? It's as follows. So in each iteration, first of all, the agent receives the current estimate from the server, namely xk. Right, that's what this says here. Having received the estimate, then the server, the agent, we're talking about agent I here. So once agent I receives the estimate xk from the server, it can compute this gradient of its own local cost function fi at that value xk. And then the agent takes a step in the direction, or the negative direction of that gradient. And we saw this kind of expression previously. We have the current estimate xk, you subtract from it the gradient, but multiplied by the step size, lambda k. And this value that the agent is computing, let's call it yk. And then that y value is sent back to the server. So in this manner, the server will receive y1 from agent 1, y2 from agent 2, and y3 from agent 3, or how many ever server agents you have in the system. Having received those, now this y1, y2, y3 are not going to be identical because each agent is using its own gradient. So the server essentially combines these y values. In this case, is computing xk plus 1 equal to 1 over n, the average of these different y values. And you can imagine variations on the algorithm, but roughly this is the flavor of all the solutions, that what the agents are sending to the server is not their function. They're not sending their gradients. What they're sending are these updated values of the estimates back to the server. And then the server has to combine the estimates coming back from all the different agents. So this is what, like I said, each agent is doing in the algorithm I just presented. Now, in this particular step, so in each iteration, the agent receives xk from the server, does this computation where it computes the gradient once and uploads the value back to the server or sends it back to the server. This computation is happening once, but we can actually take multiple steps, meaning that if you are suppose agent one, then you would receive xk from the server, then you would compute xk minus lambda k gradient of f1 at xk. Let's call this value z1 for future reference. So that's one step of this gradient descent algorithm performed at agent one. Then he can take a second step. It can take this value, right? It has just computed, and then subtract from that lambda k gradient of f1 at z1, the value that we just computed here. So effectively, what's happening, the agent receives a value xk from the server, and then it just performs two iterations of the centralized gradient descent that we saw previously in the previous lecture. In this example, two iterations so that that algorithm using f1x as the cost function, it can compute the gradients from that. Now you can replace the two steps by 3, 4, 5, how many ever you want, and then send back the net result of all those steps back to the server. And each agent can do the same thing. So maybe each agent takes 10 steps using its own cost function and then sends it back to the server, and the server can then merge all these estimates as shown on the last slide. So you can do, there are generalizations of the basic idea. And you can even get a stochastic version by changing the algorithm slightly. So if I go back, the algorithm says that in each iteration, each agent does this. Each agent I performs this iteration. Instead, in the stochastic case, so if you have a million agents, they all have to do this in one iteration. In the stochastic case, instead of insisting that every agent do this, the server can ask a subset of the agents to take part in the current iteration. So the server picks a subset of the agents somehow, and those agents in that subset will perform the iteration, send back the estimate, and now they should not be 1 over n anymore. If the subset size is, let's say, s, it should be 1 over s, where s is the number of agents in that subset. Okay, so I should not have said 1 over n here. Should I said 1 over s, where s is the number of agents in the subsets chosen by the server. But that's the stochastic version, because now we are not using all the agents simultaneously. This is analogous to the centralized case where the exact gradient method will compute the gradient, for example, for machine learning, for the loss at all the data items, where the stochastic case might pick a subset of the data items and compute the loss for the corresponding loss functions. It's similar here. I may have 100 agents or 1,000,000 agents. The subset may only contains 1% of the population of the agents, and they will participate in this computation. So again, this n is not n anymore. It's the number of agents that are included in the subset. So like I said earlier, the uniform weights are important. So if you go back here, if, for instance, we include agent 1 in every iteration, meaning anytime I pick a subset, agent 1 is always there, whereas agent 2 is included only half the time. Then what we're going to have is that these weights that the different agents are getting are not going to be equal anymore, because I chose agent 1 in my subset much more frequently than agent 2. The gradients effectively get those different agents effectively get different importance, different frequency of sampling, and therefore the cost function we'll end up minimizing won't be the original cost function anymore. It will be some other weighted average of the initial cost function. And the weights might depend on how you are sampling the different agents. So you have to be careful in how you sample those subsets so that you actually have a uniform weight instead of a non-uniform weight. Okay, so that was a so-called federated architecture. The distributed version architecture is not really that different. At least conceptually, they sound the same, with one subtle difference, or maybe not so subtle difference. So let's talk about that. The picture looks similar to before. There is a server that maintains an estimate, which is initially x0, 0 is the initial time, xk is the value at the server after k iterations. And as before, in each iteration, the server will send the current value of xk to all the agents, all of them. And then each agent I, once it receives this value, the current estimate from the server, it will send back the gradient itself to the server. Unlike the federated case where the agent actually took a local step, updated the estimate, maybe once or even more than once perhaps. Here we are not doing that, we are uploading the gradient itself. I'm sending the gradient back to the server. And now the server's job is to combine all these gradients. So that's what the server is doing here. He gets all these gradients from the agents, computes the sum. It can do that now because the server has all these gradients. It makes it easier. And then the server can take our standard gradient descent step to compute xk plus 1. So conceptually, this is not terribly different, but in practice, it is different because in one case, you're sending gradients. In other case, you're sending estimates. Okay, so let's go to the stochastic version of this algorithm. It's very similar to the federated case. Now, instead of requesting gradients from all the agents in the system, the server can request gradients from maybe just one agent at a time or a subset of them at a time. And then the summation that the server is going to perform once these gradients are received will be over that subset, not over all the agents, just over that subset. And here again, you have to be careful about making sure that you're maintaining a uniform distribution somehow when you're doing stochastic gradient descent. I did not talk about the issue of the maintaining uniformity of weights for the federated case, maybe not as much, but the issue applies to both the settings. So here is the issue. When the server picks a subset of the agents, that's one source of randomization for this stochastic gradient algorithm, right? The stochastic method rather. The server is choosing a random subset of agents, and we want to maintain uniformity across all the agents. So that's one source of randomness you have to be careful about. And then each agent, right, when it participates in a given iteration, when the agent is chosen to be in that subset, then the agent has to compute the gradient, for example, and send it back to the server in the second example of the server-based architecture. And that gradient is computed, if you are thinking of machine learning, then the gradient is computed over the data that resides locally at that particular agent, over all the data items. So it's the gradient of the loss summed over all the items at that agent. We can do a second stochastic step there as well, meaning second source of randomness, where the agent may not compute gradient over all the items it has. Maybe it can pick a subset of the items it has and compute the gradient over the loss functions corresponding to that subset of the data items. And when you're choosing these subsets randomly, subsets of agents, and then subsets of data items at each agent, you have to be careful so that you don't lose the uniformity of weights that I alluded to previously, now more than once. In this example here, that agent, this is the agent that was chosen in a given iteration. In that subset, there's only one agent, number 2, and that agent happens to choose these 3 items to compute the loss function, the gradient of the loss function over. So you will compute the loss for these 3 items and then compute the gradient of those 3, the sum of those 3 loss functions. And like I said, we have to maintain uniformity across those because of the reason we saw earlier. So this gives rise to 2 different cases for stochastic machine learning that we should talk about a little bit more. So one is called so-called heterogeneous case, the other is homogeneous case. So in the heterogeneous case, effectively, each agent has access to a different subset of the data set. That's one way to think about it. Or another way to think about it is that the cost functions that they have are distinct. Or yet another way to think about it is that when they draw gradients, or when they draw data items to compute the gradients they're drawing the data items with different distributions. So these are all, in a sense, equivalent views of the problem. But the point, so one simple situation may be that each agent represents a hospital, and each hospital has its own data set. For example, one hospital may have a data set that relates to heart disease, another hospital may have data set that relates to cancer and things like that. And you're merging all this to produce a model. And clearly, there is diversity of data here, the cost functions will be different because of that, or the gradients these different agents compute will be different because of that as well. Having multiple agents in both settings, homogeneous and heterogeneous, gives you parallelism. So even though we call these systems distributed, there was initial interest in these settings for the parallelism it affords, meaning you're using multiple agents, which are actually multiple computers with their own processing capacity. And by having many agents, you get the parallelism that speeds up the training because you're computing many gradients in parallel. The homogeneous case is the other extreme where all the agents are basically identical, at least in expectation, meaning if you look at the gradients that they're able to provide to the server, if you take the expected value of the gradients, they're going to be identical. So in a way, the agents are interchangeable. And again, the availability of all those agents provides parallelism that speeds up the computation. In this case, the computation to determine the argmin of the global cost function. If you like to learn more about these kinds of architectures, there are, of course, many papers about these. But this particular paper is very nice, and it gives an overview of the different methods, but in particular, the stochastic algorithms for machine learning. So there are many variations on the basic schemes that we discussed. The scheme we discussed is synchronous in the sense that the server waits for all the agents or the subset of the agents that it has chosen before it will make progress. Asynchronous algorithms are a little bit different, and we'll talk about those next. There are ways of improving efficiency of the algorithm by reducing communication, in particular by compressing those gradients in the second scheme that they have that we discussed. But there are other ways of compressing things as well. And the algorithms that we're discussing for the most part are shared, rather message passing, meaning the server and the agents communicate by message passing. And I will discuss what that might mean. But there is a different method for them to communicate through shared memory. And we'll briefly talk about the impact of using messages versus shared memory for communication, the impact they may have on the algorithm behavior. So the synchronous algorithms, in the very first algorithm we discussed, the server talks to all the agents and then waits for all the agents to respond. Now, if the server is talking to, let's say, 10, 50, 100, or even 1 million agents, if you're going to wait for everyone to respond, then the speed, the time it takes to complete one iteration is dictated by the slowest agent, right? So if I send a message to 100 people and then I wait for all 100 to reply, then the slowest person will delay my iteration because I cannot take the next step. In this case, in optimization, the computing the next estimate until I know all the gradients, for example, from all the agents. So these stragglers, the slow agents, are actually bad for your throughput, meaning the rate at which you're able to perform computations and then eventually converge to a solution. And to get around the problem of slow agents, one uses so-called asynchronous computations. So this is the example we solved here. And like I said, if you have to wait for everybody, then that may not be the most efficient solution. What if these two respond really quickly, and then this one is very, very slow for some reason? This happens in computers. Occasionally, some computers may be overloaded, and therefore they're not able to respond. There could be maybe one machine fails and then has to recover, so that takes time as well. So there could be many reasons why a machine, one of the agents, maybe one or more agents may be slow. It could be something happening at the agent itself. It could be on the communication channel from the agent to the server, but somehow it may happen that some agents are very slow. So that's the reason to think about asynchrony. And so I want to define what asynchrony means. The term asynchronous is used in different communities slightly differently. So distributed algorithms community, the traditional distributed computing theory community. For example, there's a conference called ACM Portsea. You will get papers from this community at Portsea. And actually I belong to that community myself. So when we say that a system is asynchronous or the network is asynchronous, it means that even though the delays for an operation may be finite, they're unbounded. So for example, if I send you a message and I say that the network is asynchronous, it's guaranteed, at least so long as so long as I assume a reliable channel, that the message will eventually get there. But I cannot tell you a priori how long it will take. So for example, if I wait, I send you a message and then I expect a reply from you. If I knew in a synchronous system, you might know this, that the delay in each direction is no more than 30 minutes. Then I can say, look, within an hour, I should get your reply. There is an upper bound of 1 hour. When I send you a message, I expect a reply. In an asynchronous system, such a bound doesn't exist. So I could wait for an hour and then give up, and the reply may come just a minute later. Or maybe I wait for 10 hours and the message doesn't come, but maybe it comes just a little bit later. So there's no fixed or prior bound that I can choose that will guarantee that the reply will come back within that time. And same thing for computation. If the computation is asynchronous and you ask me to perform a certain set of instructions, then in an asynchronous system, I cannot give you a fixed duration of time within which that computation will be complete. So that sounds like a very extreme assumption, but that's the model we often use to develop a particular class of results that are useful in practice, so-called impossibility results, and often designing algorithms that can circumvent the problems caused by asynchrony. In the communities where the work on distributed optimization tends to happen more, the model, even though someone may call the network asynchronous, it's very often the case that the delays are assumed to be bounded. Meaning you can say, look, if I send you a message in round number 1 in the first iteration, then you will receive it by the time you're performing your 10th iteration. Some such constraint is assumed, or the constraint may be stated slightly differently. And when there are not explicit bounded delay constraints, there may be a very strong assumptions on how the delays are distributed. But the point being that these two groups of people are not really assuming the same thing when they refer to asynchronous system. So generally, we'll just assume for the discussion here that the delays are bounded. And yet, so delay bound could be 1 day. So imagine that normally the message should come from you to me within 10 milliseconds. And I tell you the delay is no more than a day. Yes, it's bounded, but that doesn't mean you want to wait for a day to get a reply from you. So you want to be able to make progress to the next round without having to wait up to the bounded value. So meaning it's true that even if you have a bound, it's true that this guy will respond within the bound. But if this response comes back within 1 millisecond, and like I said, maybe this delay is 1 hour, the bound, the server doesn't really want to wait for 1 hour for this one guy. He wants to proceed because everybody else has responded within 10 milliseconds. And the question is, can you design algorithms that allow you to make progress without waiting for everybody? So even though there may be a bound, it may not really help you a whole lot in terms of, you cannot really wait for the bound itself because the bound may be too large. So as a practical matter, in the setting we're looking at, this is a reasonable assumption, actually. All right, so the general idea is actually very simple. Let's say the distributed architecture we saw earlier, where the server sends the estimate to all the agents. All the agents are supposed to compute gradients at that estimate and send back the gradient to the server, all of them. And the server waits for everybody in the synchronous setting. Here in the asynchronous setting, basically the server is going to start taking a step, or rather take the step as soon as it hears from just one agent, perhaps. Okay, so actually I call that client. This client and agent are the same thing in my jargon here. So here is the algorithm. And for the asynchronous case, I'm not presenting the algorithms very precisely, mostly because there are many variations on the algorithm that all look slightly different. And the details are not terribly important for the discussion here. At the level that I'm discussing the algorithms, the minute details are not critical. So what's the algorithm? Again, the agent will send an estimate to the clients. And if you're one of the clients, let's say client I, when you receive an estimate from the server, you compute a gradient at that estimate and send back the estimate, the gradient to the server. And then the server has a current estimate from which it will subtract whatever gradient it is receiving. I put a question mark there, and multiply by the step size to compute the new estimate. And I have kind of omitted the subscript here for time because I don't really know. There may be a mismatch between, in fact, maybe I should not write this K here either. there may be a mismatch between, so what may happen, let me rephrase this. What may happen is that, so let's say that server has estimate x1. He sends the estimate x1 to both of them. And now this guy sends back the gradient at x1. And now the server has computed x2. Whereas what this fellow received is x1. But because this agent has not received x2 yet, what he may send back is actually the gradient of function 2 at x1. Now remember that the agent has already taken a step and computed x2. But yet, despite this fact, the server can actually use the gradient from agent 2, and this step is going to be a step size, let's call it lambda, or lambda 2, if you will, and the gradient of function 2 at x1, even though this value here is x2. So there is a bit of a mismatch between which estimate I'm updating and the gradient I'm receiving. And that mismatch can become a problem if the delays are arbitrarily large. If the delays are bounded, then you can actually use these mismatching values and yet end up in the right answer. And typically, for that claim to hold true, these algorithms will assume that the functions are alpha smooth, which is to say that the gradients are Lipschitz continuous, and that helps. And then the delays are bounded, so which means that this value of x and the value of x used to compute the gradient are not that far apart in time. And because the function is Lipschitz, those gradients, even if this gradient was at the true value, meaning at x2 instead of x1, those gradients are not going to be that different just because the function is Lipschitz continuous. So I'm waving my hands a lot, but the general idea is that asynchrony, even if the system is asynchronous, the server actually can make rapid progress by using information as it arrives and by being careful about, of course, making the right assumptions. And in many cases, you have to choose these weights carefully. As long as you're careful about making sure the system satisfies these right assumptions and choose the weights correctly, you can actually get to the right answer. And so the uniform weights comes back here as well. The issue of uniform weights is important in almost anything except the purely synchronous case. So because different agents may experience different delays, you have to somehow make sure the weights are somehow uniform. So there are a couple of solutions I have seen used, and actually I'm discussing them here without citing the papers. I'll try to find the relevant references and put them up on my website on the page for the tutorial, or update the slides at a later time. But one idea is that I'm going to use a step size, which is here. So for example, imagine that the server, this is server S, here is agent 2. Imagine that I am the server now, heard from agent 2 10 updates ago. And now I have heard from, right? So maybe the last time I heard from agent 2 was when I performed the 5th update. And now I'm performing 15th update and I have heard from agent 2 again. So there's a gap of 10 iterations in between. And then I'm going to use a step size that varies. So if there's a long time that has elapsed, then I want to make the step size larger, actually, not inversely. So in a sense, if I'm hearing from you less often, every time I hear from you, I need to give you more importance. And so in a sense, the step size should scale with how much time has elapsed since I heard from you. So that's one general idea. That the way I present it is not very precise, but you get, hopefully the high level bit is clear, that you can adapt these step sizes so that each agent gets equal importance, meaning if you take the multipliers here, if we add them up, you get to the same value over large intervals of time. The other option, which is conceptually much simpler, is that imagine that the server receives one gradient and then making an update to the local state. It's only heard from one, and there may be 100 agents. So 99 of them, all the server has are the old values that he received from those agents in the past. So this method says the summation here is over all the agents, actually. And for each agent, the server will use the most recent value, right, received from the corresponding agent. So maybe from agent number 3, I'm receiving the latest value. From agent number 1, I may have received the gradient 2 iterations ago. Agent number 7, I may have heard from him 7 iterations ago, and so on. That's the most recent gradients received. We just use all the most recent gradients. So in a sense, all the weights are going to be uniform, right? Because we are accounting for every agent in every iteration, except that some gradients are a little bit stale. But if you assume bounded delay, the staleness is bounded as well. And that bounded staleness actually helps in proving correctness of these algorithms. So I mentioned earlier that the communication between server and the agents, I'm implicitly assuming message passing, but one can actually use shared memory. So what does that really mean? What does message passing mean? So pictorial is something like this. You suppose you're server S, and I am agent number 1. You want to send me the current value of xk, right? So the current value of xk is here at the server. Remember, the server itself has to store the current value of xk in the memory. Now, xk may be a very high dimensional vector, so it takes a lot of space potentially. But when server wants to send xk to me, it forms a message. It's like taking an envelope and putting the letter in there. Similar thing happens in a network too. The server has to form a message that goes over the network, perhaps over the internet, that includes this particular parameter vector, xk. And when the client receives it, agent 1 receives it, now it can access the entire vector xk. Now, because of the way the server is composing the messages, the server will have a consistent view of the vector, which is to say, imagine that the server initially has value xk, which maybe it has 4 elements, and it computes xk plus 1, also has 4 elements. And when the server is sending xk plus 1 to somebody, so let me actually change the color here. Let's say this vector is blue and this vector is red. What will not happen is the following. What will not happen when a message is sent to somebody else is this. An agent should not receive the first 2 elements from this vector and the bottom 2 elements from this vector. This will not happen in the message passing scenario because the server has complete control on what it is sending. So server updates these vectors atomically, as in the sense that when the server gets the gradient from one particular agent, it can update the whole vector using that gradient and then apply the next gradient and so on. And when it wants to send the vector to somebody else, it does that after the current computation of the vector is complete, and then it can send the whole vector to somebody else, in particular agent 1. So message passing behaves as your intuition thinks, rather you intuitively believe things should behave, right? But shared memory can behave in ways that is not intuitive, it behaves somewhat differently. So perhaps the shared memory is more interesting, in particular asynchronous shared memory. So the asynchronous part of shared memory is that the idea is the same. There are delays that are unpredictable. But here is a pictorial view of what's happening. I think I have the wrong picture. Yeah, let's look at this picture. So you have the server is now replaced by shared memory. Of course, there is a server that is implementing shared memory. You can view it like that. But the key is that this vector x, because it's potentially very long, what each agent reads, so if the vector x has 3 elements, let's say vector element number 1, element number 2, element number 3, this particular agent is reading the vector 1 element at a time. Imagine that there are 100 elements, so you want to, you have your agent number 1, you want to read the vector, all the 100 elements, then you say read x1, read the first element of x, then read x2, then read x3, then read x4. It may not be possible in this system to simply say read x and get a consistent snapshot of that vector all at once, because this vector may be just too large to perform an atomic operation like this. And in particular, people build systems where one actually runs the machine learning without having this kind of atomicity for read and write operations, and yet actually get the correct result. That's the interesting part. But what can cause problems is the following. Because you're reading the vector one element at a time. So I read the vector first element first, then second, then third, then fourth, then fifth. What may happen is that by the time I finish reading the first 5 elements, somebody may have modified the sixth element using a new gradient. And now when I read the element number 6, I got the old values of first 5 gradients, but for sixth gradient, I'm getting the new value. Okay, so you might read a vector where different elements of the vector have different degrees of staleness. And let me try to illustrate that with an example. So imagine that the current initial value of the state of the server in the shared memory now, the server is implementing shared memory, is 102. There are 3 elements in this vector x. Now, this gradient step is performed using shared memory operations as well. In the shared memory setting, you have to visualize the agent not sending the gradient to anybody, but actually performing this operation element-wise. Just the same way I read things one element at a time, this operation requires the agent to update one element of the vector at a time. So this is actually a vector. X is a vector, the gradient is a vector. So you can imagine the two vectors lined up. You compute the first element of the new vector, the first element of x minus lambda times the first element of gradient f1x. Then the second element, third, and so on, right? We are doing this. And so what's happened here is that for some reason, that agent number 1 has managed to perform these updates. It's a write operation into the memory. It's actually a read. It's a modifier. You're reading a value, modifying and writing back. So somehow, because of the variations in speed of the updates, the agent has managed to update element number 1 and element number 3. If you prefer these elements to be consecutive, then you could imagine that element number 1 is modified and 2 is modified, but 3 is not. But I'm saying here 1 is modified and 3 is modified, but not 2. That could happen too. Now, eventually, this will be modified too, right? It won't be 0 anymore. It will change color, meaning it will have the new value. But what may happen is that some other agent may come along and read this vector as it is before this element gets modified, the second element gets modified. And this is what I meant by inconsistency earlier. This agent 2 has 2 elements of this new vector that are updated, but the element number 2, the middle one, is the old value that agent 2 is reading. Now, it's not terribly old, right? You can, if you have some assumptions or not just assumption, but if it is true that these updates have bounded delay, then how stale this value is will be also bounded, right? So it really depends on what assumptions you're able to make. But nevertheless, the vector is not consistent. And then the question naturally is, what is the price of this kind of inconsistency? What's the price of asynchrony? And this paper has some results about that. In fact, it tells you how to quantify the price of asynchrony in the shared memory setting. We won't, unfortunately, have the time to get into details of this. In fact, as you may have noticed already, I'm not presenting any of these algorithms in any great detail, not today at least. But what I'm thinking now, having done the first lecture and the second lecture today, that I may actually present a couple of these solutions in more detail and even go over the proofs of one asynchronous algorithm perhaps, and maybe one stochastic algorithm as well. But that won't happen in the first 6 lectures I have planned. I will have to add more lectures beyond those for the proofs and more details of the algorithm. So I said earlier that for that initial centralized, the server-based rather scheme that was synchronous, there are many variations possible. One was stochastic method. The other is asynchronous. And there are many other variations too that I'm not talking about. A third variation that just one slide on it is gradient compression. So if you think of the algorithm where each agent computes a gradient and sends it to the server, this gradient may be very expensive to send. If your parameter vector x has 1 million parameters, then the gradient will have 1 million elements in it. And what if half of these are just 0? Then clearly you don't need to keep sending zeros all the time. You can compress the zeros away somehow. But more importantly, what may happen is that this is the server, this is the agent number 1. This agent has sent, let's say, gradient of f1 at the value of x1. And now it is sending gradient of f1 at value x2. So x1 and x2 are different. So the gradients may be different or could be very different. But in practice, it may turn out that if these are the two gradients, that maybe these two entries are the same and these entries are the ones that differ. Or even if the middle two entries are not identical, they are very close to each other. And one way to compress the gradient, the second gradient, is to say the second gradient only differs from the first gradient in position 1 and position 4 in significant ways. And here is the difference. So you can essentially compress the second gradient by taking the difference between the two gradients and sending only the most significant information. And there are many variations on the compression algorithms. There are one that just says, let's just send the top k elements of the vector, the gradient vector. And then there are all kinds of other subtle differences. In the equation that we wrote for the update, we actually are treating all the values as real numbers. But in practice, these are all discrete numbers because we have finite precision. And maybe you don't need a very high precision depending on what you're trying to do. And then the question becomes, if you have finite precision, you're already making some approximations on the gradients you're sending. Can you actually systematically decrease the precision of the gradients that you send and yet achieve correct results? And there are modifications on the basic scheme that utilize that trick to send fewer bits per gradient, essentially, and still achieve a result that is sufficiently accurate within the accuracy that you desire. And I'll try to add some papers on gradient compression as well in my reading list at some point. Okay, so we talked about the server-based scheme, and now I want to get to the peer-to-peer architecture next. And there I'll spend a little bit more time because it's a little bit surprising that the peer-to-peer algorithm actually works. So for the peer-to-peer setting, you might see different terminologies being used in the literature. Sometimes these algorithms are called multi-agent, sometimes they're called peer-to-peer, sometimes they're called decentralized. I often just call them distributed. But the architecture looks something like this, where you have agents, in this example 5, that are connected to each other by a network. In the special case, the network might be a complete graph, meaning everybody can talk to everybody else directly. Whereas in this particular picture, agent 5 only interacts with agent 1, agent 3 interacts with agents 2 and 1, and so on. So the network tells you how the interaction happens. So it's expressed by means of a graph. This graph is undirected in the sense that if 1 can talk to agent 3, then 3 can talk to agent 1. But there are generalizations of this where the graph actually is directed, meaning agent 5 may be able to send message to 1, but not vice versa. Of course, you need these graphs to have some desirable properties for the algorithm to work, but this is the general architecture. So for this particular architecture, there are, in fact, 2 types of solutions, or at least 2 types of solutions that have been developed. Here is one version that is quite interesting, but we won't discuss it in this tutorial. So in this particular version, there is just one cost function, let's call it fx, and the agents are cooperating to compute argmin of fx. Fx is not a summation of fix anymore in this particular version. However, in this distributed setting, the reason there are multiple agents and we're able to use the multiple agents to perhaps speed up the solution is by requiring each agent I to estimate the ith element of the argmin of this single cost function fx. So for example, agent 3 is going to keep track of x3, the third element of vector x, agent 4 is going to keep track of fourth element of vector x, and so on. The variation that we will consider here is compatible with everything we discussed so far. One at the bottom here, that agent I knows function fix. It doesn't know the other cost functions of other agents. And the agents are going to cooperate to find argmin of the summation of all the local cost functions. And in fact, all the agents will learn that solution that they're computing collaboratively. So in effect, what they achieve is something called consensus. Consensus just means agreeing on something, but what they're agreeing on is this value. And when I say agree on, they actually learn that value. So they all learn an identical answer, a vector x that is equal to, that's in argmin of sigma fi x. So this particular problem is very well studied for more than 30 years by now. There are many, many variations on the theme. There are synchronous algorithms, there are asynchronous algorithms. There are algorithms that try to reduce communication by some other means. There are, maybe discretizing the communication, event-triggered communication. There are papers that allow for links to be lossy, meaning I send you a message, but you don't receive it, or assume the links are reliable. The network may be static or time varying, right? There are many variations of this sort. We will just look at one setting, the simplest one. The network is synchronous, the system is synchronous, and the links are error-free. And that will already give you some insights into how different this setting is from the centralized server, not centralized, but the server-based distributed architecture that we saw. But before I can tell you about optimization in this setting, I need to explain something called average consensus in the setting of this peer-to-peer or decentralized architecture. The reason to do that is that the solution of optimization problem, the distributed solution in this peer-to-peer network uses the solution of average consensus as a building block. And so if you understand the average consensus algorithm, then the optimization algorithm is just a small variation of that. So let's talk about it. So here is the problem formulation for average consensus. So for the moment, forget about optimization, forget that the agents have cost functions, fi, x, and so on. Instead, each agent has an input, which is some scalar or vector, depending on your setting. So for example, if you recall my picture where the people wanted to meet somewhere, right? So we can use average consensus for that as well. So you could say, look, this is my location. Suppose this is me. I'm at location Z1. Now, if you're in the city, Z1 may be a two-dimensional coordinate. Suppose that at the intersection of two streets, then you could say I'm at the intersection of Main and 6th Streets, right? So each of us has a coordinate. Of course, what we need for this particular problem is a vector that is a real number. So GPS coordinate will do perhaps, but some coordinate, let's say it's a two-dimensional vector. That's the input for the algorithm from each node, but you can interpret that as a vector that specifies the coordinate of each of these nodes, agents in this example with 3 agents. And what I want to compute is the average of Z1, Z2, Z3, which may be somewhere here. And that's the goal. That's the output of an average consensus algorithm. So input is some value. The value may actually be a vector if the problem is, if your arguments are vector, or it could be scalar. The solution doesn't depend on whether the argument is a scalar or a vector. Okay, so that's the goal. Of course, that's the trivial solution for computing average is that we all send our input to somebody, to a central entity like a server, and then the server computes the average and tells everybody. But no, we are not going to do that. We want to make our life a little bit more complicated. And so these are my 3 agents, and I want to compute the average, like I said. The reason these are shown as birds, by the way, I took this slide from a different talk I gave some time back because there's a problem called flocking, where people focus on computing solutions of this sort, and that's why I have drawn birds here. But these are just my agents in this system. Okay, so there are 3 agents in this example. And in this example, the agents are connected by a network like this. And if I were to draw the network a little bit simpler, it would look like this. Okay, this is my graph. There are 3 agents. Let's call them ABC, or you could call them 1, 2, 3. But in my illustrations, I'm calling them ABC. And they're connected by this simple network. So B and C talk to each other. C and A can talk to each other, but not A and B. So that link is missing from this graph. So it's not a complete graph. And each agent has an input. So for convenience, this is agent A. I'm calling the value at that agent also A. It's lowercase, but it's still A. Okay? This is agent B at the top and agent C in the middle. Now, initially, the value at agent C is just the input of agent C. So what's happening basically, each agent is maintaining this value what we call estimate in the previous algorithm. You can call it estimate here too, but just a state variable that each agent is maintaining. The state variable is initially the input of that agent, and now the state variable will be updated during an iterative algorithm. And so the iterative algorithm is very simple. In fact, the algorithm is described by these equations here. So let's read those. And for simplicity, I have removed the time indices from these equations, but I will add them back as we discuss further. But let's say the initial values, suppose we add subscript 0 to the initial values. So actually these are, let me write this equation again here just for clarity. Or I think let me do it this way. B, I'm going to use brackets for time later on. So let me just start doing that here. Okay, so this equation, I've rewritten that by adding time. So in the bracket, now I have the time index. It's a different notation than I have used before. So this just says that the new value of B after one iteration is 3/4 the initial value of B plus 1/4 the initial value of C. Okay, that's what this equation says. And similarly here, A1 equal to, this is A0 and this is C0. Okay, similarly for equation for C as well. So that's a very simple set of updates. So how would we implement these updates in practice? Because it's a network now. If B needs the value C, how is it going to get that? This node will send to him the current value of C, which is C0. 0 in bracket is the time. And similarly, he's going to send C0 to this guy. And this fellow is going to send to him A0. And node B will send B0 to agent C, right? And this is how they learn each other's current values. Then they update, perform these equations. They all compute C1, B1, and A1. Okay, this is one iteration of the algorithm. Then you repeat to compute B2, for example. B2 will be equal to 3/4 B1. And node B already knows B1 because he computed it, plus 1/4 C1. How does node B get C1? This guy will have to send the new value of C, which is C1, to node B now. That's how node B will learn the new value of C from node C or agent C. Right? So the communication is required for the agents to learn from each other their current state variable or current estimate. Okay, so the algorithm is very simple. It's just taking linear or weighted averages of, so if I'm agent B, I'm taking my new value, my new state variable is the weighted average of my own current value and the values of my neighbors. It's a weighted average because 3/4 plus 1/4 adds to a 1. 3/4 plus 1/4 is 1, and here a 1/4, 1/4, 1/2 adds to a 1. So I've chosen these weights carefully, and you'll see in a minute what those weights actually, how the weights are chosen. But that's all that's happening. This is also a weighted average of the current value of node C and the current values of the values of the neighbors of node C. So the algorithm is very local in the sense that each agent only needs to talk to his near adjacent nodes in the graph and get the values from them, and then he can compute the new value, the local value. And just keep repeating this for a long time. As time progresses, these values will keep changing. So for instance, if the values here, this was B, C, and A, if values B, C, and A are initially 2, 1, and 6, then by applying the iteration, the new value of B will become 7/4, and this is 19/4. You can verify this math, but all I'm doing is applying this equation on the previous slide here to the specific values of A, B, and C. Now that, so this is B1, A1, and then C1. And now you can take these values and update the variables yet again to compute B2, A2, and C2, and so on. So one observation to make is that the initial values, if you write them down, 1, 2, and 6, how far apart are they? The max minus min value is 5, whereas here the minimum value is 7/4, and the maximum value is 19/4. So the difference is equal to 12/4 is equal to 3. So what you notice is that in this example, at least, the gap or the distance between the maximum value and the minimum value has decreased by a certain amount. Now, in my example, each of the state variables is a scalar, a single real number. In general, this A, B, and C would be vectors. And this computation on the last slide will be done element-wise, meaning the first element of, let me see, 3/4 plus. So you will take the first element of this vector, the first element of this vector, multiply this guy by 3/4, this guy by 1/4, add them up, and that's how you get this element of the new vector. So you're just applying this equation one element at a time. And if you looked at the distance between the, if you take the maximum distance between A, B, and C, now when you have vectors, you have to define what distance means. Maybe we take the L2 norm of the difference between two vectors, that difference will keep shrinking as well. You can actually prove that as long as these weights are chosen carefully, and I will tell you very soon how. But the illustration I have is for scalars, but the result will apply for vectors too. So it turns out that if you run this algorithm longer, meaning I showed you only one iteration, if you do 2, 3, 4, 5, and for a while, these numbers will start getting closer and closer and closer. The gap between the max and the min will become smaller and smaller and smaller, which is to say, as time goes to infinity, they'll become equal. Or if you want these values to come within 0.001, then you can determine exactly how many iterations it will take, a bound on the number of iterations it will take for them to come within that 0.001. So you can make them as close as you want. And that's what we call consensus in this setting. Consensus just means agreeing on something. But it's not just that they're getting the same value. The value has some meaning. The value is actually the average of the inputs at all the nodes, the initial values. In my example, there are 1, 2, and 6. So as time goes to infinity, each of these local state variables will become equal to average of 1, 2, and 6, namely equal to 3. And this is true and under some assumptions about these weights. And again, I have not told you what they are, but this is a really pretty algorithm. The first time I saw this algorithm, I was really impressed. I didn't know exactly what it is doing. The proof of why it works is not that complicated. Actually, it only takes about 15, 20 minutes. But unfortunately, we won't have time for that here today. So what I want to show you is just a way of writing this algorithm in a more compact form that sheds some light on what's happening. So I have written these three equations now in the matrix form. So remember, I call this value, initial value of B as B0, initial value of C as C0. If you write these values as a vector, right? This is a vector of the three initial values. And this is a vector of values of A, B, and C after one iteration, okay? So what I've done in this slide is actually to use a slightly more compact notation for this vector. I write it as ABC with a subscript with this index 1 here. And then this vector I'm writing is here, again, ABC. Those ABC could be replaced by numbers, but the 0 subscript of the index is this time index here. Okay, so that's just a shorthand. ABC0 is just a shorthand for the initial values of A, B, and C. And this is a shorthand for values of A, B, and C after one iteration. So let me erase all this. So now there's a matrix here. Let's look at the first row. What happens if you multiply this row with this column? You're multiplying 3/4 with A0 plus 0 times, so that goes away, plus 1/4 times C0. But that's nothing but this equation applied to the first iteration. B, actually not this one, I'm sorry. This one, you're looking at A on the left, it's A. So the equation for the update of A is captured now using the first row of this matrix. Similarly, let's look at the last row. On the left is C. So we are looking at this equation here. If you multiply this row with this column, then multiplying 1/4 times A0, the initial value of A, plus 1/4 times B0, plus 1/2 times C0. That's just this. If I replace A with A0, B with B0, and so on. On the left, it will be C1, which is precisely what I have here. And long story short, all I have done is to take this algorithm and return it in a much more compact format using this matrix that we are going to refer to as matrix M. Okay, so I have not done anything new. The algorithm is actually distributed. We are not performing matrix multiplication somewhere centrally, right? We're just performing, each agent is performing his own local update through talking to the neighbors and computing these new values and so on. This is just an interpretation of what's happening or an equivalent representation of what's happening, but we can analyze that now. It's just now just, we can just do some algebra to prove what's happening. So what you observe about this particular matrix are three things. One is that all these numbers are non-negative. That's by choice, because what I'm trying to do is to find, essentially I'm trying to interpolate between these own value and the neighbor's value. So these are non-negative numbers, but more importantly, they're adding up to one, so that I'm computing a weighted average. So 1/4, 1/4, 1/2, they appear in each row. So each row corresponds to one of these equations. And because I want to compute a weighted average in each of these equations, that means that these weights in each row add up to a one. That's by design. Okay, so this matrix is row stochastic. Row stochastic means, first of all, that the numbers are non-negative and they all add up to a one in each row. But something else that is, you may not have noticed, that each column also adds to a one. So this matrix is also column stochastic. And that's also by construction, meaning I chose the weights deliberately so that the columns would add up to a one. So now let's consider what happens after two iterations. So the first, actually I should go back here. The first iteration now, because I'm calling this matrix M, I can write this much more compactly like this, right? So this new state after one iteration is equal to M times the initial state, the vector of initial states, right? So this is a very compact representation. Then we can ask what happens after two iterations. So on the next slide. So if this is your initial state vector, then multiplying it by M gives you the state after one iteration. And to get the state after two iterations, you multiply it by yet another M, which is to say the state of the network after two iterations is just M squared multiplied by the initial state vector. And inductively, you can see where this is going. After k iterations, the state of the system is simply equal to M to the kth power of M multiplied by the initial state vector. So what does this achieve? Let's try to, before I tell you what it achieves, let me try to write this even more compactly. Let's give this vector ABC the name X. So ABC at time 0, they're going to refer to as X bracket 0. The time is in the brackets now. So I'm mixing up the notation a little bit. I was just being lazy. I didn't want to make new slides again. And this vector after k iterations, let's call it xk, where k is in the brackets again. So this iteration, I'm going to write even more compactly now as xk, the value of vector x, which is the vector of all the states after k iterations, is just m to the power of k multiplied by the vector x at time 0. So, right. So it turns out that if the graph is connected, which means that if you look at the network, there is a path between any pair of agents in that graph. If the graph looked like this, it's not connected because there is no way you can get from here to here. Okay, so as long as there's a path in network, we're looking at undirected graphs now. But you can find conditions for directed graphs too. We will stick to undirected graphs. So the graph is connected, and this matrix M is doubly stochastic. Doubly stochastic just means it's row stochastic and column stochastic, or all the elements are non-negative, and the elements in each row add up to a 1, elements in each column add up to a 1, and the ijth element of the matrix is non-zero exactly when link ij exists. So if there is no link ij, then mij will be 0, otherwise non-zero. When those conditions are met by matrix M, then you're guaranteed that as you run the algorithm for more and more iterations, the state variables are going to approach the average over the initial state arbitrarily close. In the limit, it will be equal to average. So mathematically, what is going on, actually intuitively, this is not very hard to see what this is doing. I already pointed out that these rows adding up to a 1 basically means they're computing a weighted average, which is to say, if the rows are stochastic, then the new state, which is here, is in the convex hull of the old states. Okay, so that's one. And so each of these new values of ABC will be in the convex hull of the old values of ABC. Okay, the vectors. ABC are in general themselves vectors, although they were scalars in my example. Now the columns adding to a 1, this you may want to write down on a piece of paper and try it out. But if you take the elements on the right-hand side here, so this one I think I called this 0 and here 1. If you add up A with B with C at time 0, and then A and B and C at time 1, this summation and this summation will be equal. That's what the columns being stochastic gives you. So another way to say that is if the sum of the state variables at a given time is the mass of the system is preserved because the columns are all stochastic. And this holds for any iteration. It holds from iteration 2 to 3, 3 to 4, which is to say the total mass of the system remains constant throughout the algorithm. And these values always remain in the convex hull. So now, if all the values are becoming equal, meaning if you're achieving consensus somehow, and the total mass is preserved, then the consensus value has to be the average of the initial values. So if my columns are stochastic, and if I can prove there is consensus, then I get the claim that there is that the consensus is actually on the average for free, right? So having the row stochastic gives me consensus. Having the column stochastic guarantees that the mass is preserved together. It guarantees that I not only get consensus, but the consensus is on the actual average of the initial values. Like I said, the proof is not difficult, but I won't have the time for it. So what's happening is that this matrix M, this power of M, the kth power here, if you increase k from 0 to 1 to 2 to 3, right? Then the M to the kth power will approach this matrix. It will get closer and closer and closer to this uniform matrix, where each element of the matrix is 1/3. If you had n agents in your graph, the graph could have been much bigger. Maybe this is a graph with 5 agents, or maybe this is it, 6 agents. This would be 1/n everywhere, as long as the matrix is doubly stochastic, like I said earlier, and the graph is connected. And this is, of course, as k goes to infinity. If you look at the matrix M to the k at a finite time, it will get closer and closer to the uniform matrix. As k increases, it gets closer, even closer, right? So you can decide how close to the true average you want to be. And depending on how close you want to be, you can determine the number of iterations you need to run the algorithm to get these values to be that close to the true average. And that can be computed theoretically ahead of time. So what I discussed with you just now is the average consensus algorithm. What we really care about is distributed optimization. So with average consensus, I'm trying to find this point, which is the average of this coordinate, that coordinate, right? That's what we did. What I really care about is the minimum of this cost function, where different agents know different cost functions. And that argmin may be somewhere here, not necessarily the average of whatever input these agents may have. And the question is, how do you compute that? So the algorithm for this is actually very similar to the algorithm we saw just now. I'm going to use slightly different pictures, but the algorithm is almost the same, right? So the algorithm looks like this. You have an iterative structure like we saw before. Each agent now maintains an estimate of the final outcome, which is the argmin of this summation of the cost functions. And in each iteration, similar to the averaging algorithm, each agent will share with the neighbors his own current estimate and update his own estimate after receiving values from the neighbors as well. And in the end, as time goes to infinity, all the estimates will approach argmin of this cost function. Okay, so that's the high-level idea. What's the algorithm? The network in my example is, again, the 3-node network. I just drawn differently because I made these slides at different times. And in any given iteration, if you're agent number 3, you send to your neighbors your current value of the estimate, which I'm calling x3 in this slide. So the subscript, like I said earlier, I have a slight change in notation compared to initial slides. In the bracket, I have the iteration index of time, and the subscript for this discussion is the agent identifier. So x3 is the estimate of x maintained by agent 3. And what this slide shows is that in any given iteration, agent 3 will send his current estimate to both the neighbors. This guy will send x1 to x3 and agent 3, and agent 2 will send x2 to agent 3. Okay, so it's very similar to what happened with the average consensus. The difference is in this part. So if you're agent number 1, what do? You receive the value from agent 3, which is x3. You already know your own value of x1. Suppose we are computing xt plus 1, x at time t plus 1. So you already know the values at time t, meaning values after t rounds. I think we called it k previously, number of rounds, but it's just a change of variable there. So how do you compute the new value at node x1? This expression should look similar to before, except that I have changed the weights. I think I had 3/4 and 1/4 in my previous example. In this illustration, I've chosen different weights, but as you will see later, these weights again form a doubly stochastic matrix. That's the only thing that matters. The exact values are not important, as long as the matrix that is formed is doubly stochastic. But this part, if you ignore this altogether, this iteration is exactly what you would do for average consensus for a particular choice of weights. In this example, 2/3 and 1/3. Similarly, if you're agent 3, same idea. This part here in the blue circle is what you would do if you're doing average consensus for this choice of weights. Excuse me, 1/3, 1/3, 1/3. In my previous illustration, the weights were 1/4, 1/4, and 1/2. Here they're different, but again, these weights will also form a doubly stochastic matrix. And there's a similar equation for agent 2, which I'm not going to show just to save some space and time. So what's new here, let's go back, is this part. So this is, you can think of this as the consensus step, meaning I'm receiving values from my neighbors and I'm reconciling my value with their value through this weighted averaging process. This is sort of like the gradient descent step that we saw in the other examples, except that if you're agent number 1, all you know is function 1. Therefore, you can only compute the gradient of function 1. And you can only compute the gradient of function 1 at your current estimate. And that's what agent 1 does. It computes the gradient of his own cost function at his own current estimate and takes a step in the negative direction of that gradient. And this is our step size as before. Okay, so this looks like just like averaging. This looks just like gradient descent. And agent 3 does the same thing. This is the consensus step, which is what we did for averaging as well. And here he's taking the gradient of function 3 because he's agent 3 at the current estimate at agent 3 and taking a step in the negative direction of that gradient. And similarly, there is an equation for x2 where the gradient will be for function f2. Okay, so now the claim is that if you perform these iterations, right, you start with the initial estimates of x1, x2, x3 at the 3 agents and perform these iterations repeatedly. As time goes to infinity, all the agents will convert to the same estimate, and that estimate will in fact be the argmin of the summation of the cost function. Right? If you stop after a finite number of iterations, then you can show that maybe they're not reaching this value exactly, but you can derive claims on how close you will be to this value. And the distance from the true argmin will shrink as time progresses. With time going to infinity, distance will become 0. Right? This is the claim. I'm not going to do the proofs of this today, but let me just show you one more slide or maybe 2 more slides on what's happening. And for that, we will unroll the iteration. So this is the equations that we saw previously. Now let's call this, actually this should be x1, x2, x3. So let's stack the variables x1t, x2t, x3t, the state variables. And together, let's think of it as the vector x at time t. And similarly, these gradients I'm stacking up, and I'm going to write that this as this vector. Okay, this is just a shorthand. This is a shorthand for this. Okay, this is a shorthand for that. So there are three equations. I'm only showing two in my slides for just to keep things short. If you use that shorthand on the previous slide, those three agents collectively are performing this iteration, right? This is a very compact form representation of what's happening using these two equations and the equation for agent two. If you unroll these, you can start with, actually I already pointed out that this M here is a doubly stochastic matrix. It's different from my previous example, but that's just because I happen to reuse some old slides. As long as the graph is connected and the weights are non-zero exactly when you have an edge in the graph, and the columns are stochastic, the rows are stochastic, this algorithm will behave correctly. The exact value of M will affect the convergence rate, but not correctness of it. So this is the iteration in the compact form. You can take t equal to 0. This is the initial value. This is the value after one iteration. Then you go to t equal to 1. Then you get x2 as a function of x1. Let's replace this, this expression for x1. And what do you get? You get x2 to be equal to that. And let's do it one more time. Now you have x3 equal to this. I replace the expression for x2. And this is what you get. Now you can keep doing this. But what I wanted to observe is the following. I'm getting higher powers of m here and lower powers of m here. And this is some arbitrary division between higher powers and lower powers. What I told you earlier is that the higher powers of m are very close to the uniform distribution, meaning rather uniform metrics. Right? In my example, it was all 1/3, 1/3, 1/3. If the power of m is high enough, it's going to be close enough to the uniform matrix. The lower powers of m may not be uniform, right? Because we are not multiplied m by itself very much yet. However, in this algorithm, we are going to make alpha k decrease with time. For example, alpha k may be equal to 1 over k. So the lower order terms are being multiplied by small values of alpha, smaller compared to here, right? And these higher order terms are going to let you essentially give consensus. Whereas the lower order terms are going to be small relative to the higher order terms because these alphas are shrinking with time. And what I'm telling you here is not a proof, but it's just a very hand-wavy way of trying to argue that this algorithm will give you consensus. It still doesn't tell you why it gives you consensus on the true minimum of the global cost function, which is sigma fi(x). But it does. And that proof actually I have to omit because we don't really have time for that today. But the claim is that, like I said earlier, there is consensus. All the agents' estimate of x converges to the same value. It's a vector to the same vector, and the vector happens to be argmin of the sigma fi(x). So what I've done today is, in a very rapid way, covered a few distributed algorithms for solving or computing argmin of sigma fi(x). What we will do in the next part, maybe the next couple of hours now, is to look at these so-called Byzantine fault-tolerant algorithms that for solving the argmin sigma fi(x) problem, or I sometimes call them secure algorithms. And having done that for the next couple of hours, then we'll talk about privacy of the same type of algorithms, where you're trying to find the argmin of sigma fi(x), but you want to achieve some notion of privacy for doing so.